Hey everybody, the purpose of this video is to talk a little bit about buffers. Specifically, we want to talk about constructing a buffer of a certain pH. Before we get into the mathematics, let's remember a few things about buffers. The first is that buffers are solutions that contain significant amounts of both an acid and a base. You can really have a buffer that is made many different ways, but the two most common are ultimately buffers where you end up with a weak acid and its conjugate base, or a weak base and its conjugate acid. For the purposes of this video, we will focus on a buffer that contains a weak acid and its conjugate base. Regardless of how you prepare the buffer, what makes something a buffer is that it resists changes in pH. We can determine the pH of a buffer solution using the Henderson-Hasselbalch equation, which says that the pH of a buffer equals the pKa plus the log of the concentration of the conjugate base divided by the concentration of the acid. It's worth noting that this particular equation is only valid if the X's small approximation is also valid when talking about the acid-base equilibrium. The effective range for a buffer varies depending on which chemicals or substances are in the buffer, but generally speaking, a buffer is effective in a pH range plus or minus 1 of the pKa. So for example, if you have a weak acid in your buffer solution that has a pKa of 5, then that buffer is going to be effective at resisting changes in pH between the pHs of 4 and 6, between 4 and 6. Buffers are also most effective when the concentration of the acid and conjugate base are equal to each other. To be effective at all, those two concentrations must be within a factor of 10 of each other, but they're most effective when they are equal. Finally, buffers are also effective and most effective when the concentration of the acid and its conjugate base are as high as possible in the solution. This is because then the buffers can neutralize the maximum amount of acid or base. There are many different ways to construct a buffer of a particular pH. We'll just look at one example today and see if we can show you how to derive that buffer solution, how to create that buffer solution. So here is our scenario. We've got a chemistry graduate student, and they're given 250 milliliters of 1.4 molar acetic acid. The acetic acid, of course, is a weak acid with a Ka of 1.8 times 10 to the minus 5. And the question here now, what mass of sodium acetate should the student dissolve in the acetic acid solution to turn it into a buffer with a pH of 4.15? pH of 4.15. And we'll report our answer today to two significant figures. To do this calculation, the first thing that we need to do is calculate the pKa of the buffer, which is simply the negative log of the Ka, which in this case is 1.8 times 10 to the minus 5. So the pKa is 4.74. Now that we have the pKa and we know the desired pH, we can use the Henderson-Hasselbalch equation to help us determine the concentration of the sodium acetate that we will want in our buffer. And then we will take that concentration and we will convert it to a mass of sodium acetate, which of course is usually purchased in solid form. So from the Henderson-Hasselbalch equation, the pH, in this case our desired pH 4.15, equals the pKa 4.74 plus the log of the concentration of the base, in this case the sodium acetate, CnACH3CO2 is one way to write that, divided by the concentration of the acid, in this case acetic acid, which has a concentration, they told us, of 1.40 molar. 1.40 molar. The first step is going to be subtracting the 4.74 from both sides. If you do that, you get negative 0.59 equals the log of the base. We'll just abbreviate it B, or base here. We'll just write out base instead of writing out sodium acetate, over 1.40 molar, the concentration of the acid. Now we have to get rid of the log. To get rid of the log, we're going to take each sign and insert the power of 10, because the opposite of the log is taking the power of 10 and raising it to that power. So we get 10 to the minus 0.59 power equals 10 to the log of base over 1.4 power. The log and power of 10 cancel each other out. And so ultimately what we get is 10 to the negative 0.59 equals base. In this case, we'll reinsert now NaCH3CO2, concentration of the base, over 1.4 molar. Well, 10 to the 0.59 power to the negative 0.59 power is 0.26. Concentration of NaCH3CO2 over 1.4. And in this case, the concentration of sodium acetate is going to be 0.28 molar. And now we've got to take that 0.28 molar and we've got to convert that to grams. So 0.28 moles of NaCH3CO2 over 1 liter times 0.250 liters, which is the volume of the buffer, 250 milliliters or 0.250 liters. We'll get liters to cancel, times the molar mass of sodium acetate, which is 82.03 grams per 1 mole, calculated from the periodic table, tells us that we need to add 5.7 grams of NaCH3CO2 to this 250 milliliter buffer solution in order for the buffer to have a pH of 4.15. Of course, an assumption was made here, and that assumption was that the total volume of the buffer did not change when this solid was added. I hope this provides you with a little bit of insight about A, what buffers are, and B, one method for calculating how to construct a buffer of a certain pH.